Now, we are going to move to notation of this queuing system. We are going to show the Kendall's queuing notation. And Kendall's queuing notation is a queuing notation which describes simple queuing systems. And it is invented by Kendall in 1953. And this is basically a commonly accepted queuing notation by the whole world. Almost everybody who studies queuing theory or queuing systems, they use the Kendall's notation to describe the queues. So the format of Kendall's notation consists of 5 different sections. The first section is called section A, the second section is called section B, the third section is called C, the fourth section is called capital N, and the fifth section is called capital K. And in some extensions of the Kendall's notation, there is a sixth section as well. Now, the first section describes the interarrival time distribution of the queue. The second section describes the service time distribution of the server. So what type of distributions we have? If, for example, interarrival time distribution is an exponential distribution, then we write M in place of A. M means Markovian. And Markovian means it's a Markovian process, which means the interarrival times are exponential. And if the service times, for example, also exponentially distributed, then we also write M in place of B. So, for example, in the notation, if you see the first 2 letters, M and N, this means both the interarrival times and the service times are exponentially distributed. However, they are independent from each other. They are just exponentially distributed in separate parameter settings. And if you see a letter D, then this means a deterministic interarrival time or a deterministic service time we have. Deterministic means constant. For example, this is the coffee machine queue, and every cup is filled in 3 minutes, let's just say. In that case, in place of B here, we write capital D. And another interarrival time distribution or service time distribution can be Erlang distribution. And order K means the shape parameter is equal to K. And EK means, for example, if you write E2 in the beginning, this means the interarrival times are Erlang distributed with shape parameter 2. Second order Erlang distribution. For any other distributions other than exponential or Erlang, we write G, generally distributed. In the third section, we have C. C indicates the number of parallel servers in that queue. For example, if C is equal to 1, then this means this is a single server queue. If C is equal to 2, we have 2 servers in that queue, 2 parallel servers in a single queue. If C is infinity, then we say this is a self-service queue. Capital N is the system capacity. Capital N is the total number of people who can enter the system and be there. And if the system is at full capacity, the new arrivals cannot enter the system. Even though they arrive, they immediately leave the system. Why? Because the system is at full capacity. And K is the size of the calling population, the number of pending clients outside the system. So let's check a few examples. NM1 infinity infinity. What does that mean? The interarrival times are exponentially distributed. The service times are also exponentially distributed. There is only a single server that we get service from. The system capacity is infinity. Anybody can enter the queue as long as they want. And the pending clients, the calling population size is also infinity. Now, MG210-1000. It says the interarrival times are exponentially distributed. Service times are generally distributed with another distribution than exponential or Erlang. And there are 2 parallel servers. The system capacity is 10 and the size of the calling population is 1000. And in the third example, we have interarrival times as exponential and the service times are constant. And we have a self-service system, infinitely many servers, and both the system capacity and the size of the calling population is infinite. So this is how we read the Kendall's notation to model the queues.